Hello, it's Ryan. This is an example on a parallel circuit. It's a simple parallel circuit. I guess that's a little bit, the language isn't quite right there because we call circuits with a power supply and a single resistor simple, but this is a simple parallel circuit, meaning it only has 3 resistors in parallel. We're going to do the same as the last example where we're going to solve for the circuit. So this is an example of a parallel connection, where we're going to do the same thing, where we'll find the equivalent resistance and then all of the power dissipated, voltage across, and current through each component. So we'll just say the same as before, but we have a new picture where this time we've got our power supply and 3 resistors connected in parallel to one another instead of series. So as I've said in the past, I've never promised to be a great artist. I think we'll use the same resistance values as our previous problem. And so we know that V is 12 volts, R1 is 61 ohms, R2 was 200 ohms, and R3 was 142 ohms. We're also going to try to show the current that gets established by our power supply, but this time we have junctions, points where the current can split. In other words, points where the current ceases to exist and new currents come out. So we have I total leaving our battery. And if we have I total leaving the battery, we should habitually put I total returning to the battery. I total is incident on this first junction number 1. I total is incident on it, and out will come 2 new currents. We have one I like to say IDC and one for I1. IDC will hit junction 2, and it will split into 2 new currents. We're going to call them I2 and I3. I3 will continue through R3 and end up at junction 3. I2 and I3 will combine to create IDC again. And I1 and IDC will combine to create I total again. Something you might want to note to yourself, which is going to be true for any circuit that we can throw at you, is when we to simplify the circuit, so we'll say to simplify, oftentimes what we'll try to do is start from as far from the battery as we can and work our way toward the battery. And so I'll write that we start with the farthest components from the battery and work our way in. And I'm going to do a series of pictures to help you see what I'm saying. And so if we look at this picture, we can see that we have our power supply on the left, creating our currents that will be established throughout the entirety of our circuit. We also, if you remember from lecture, remember that most of the current will take the path of least resistance. And so right away, with that in mind, we can argue that we should get an I1 that's higher than I3 and an I3 that's higher than I2. But just because most current will take the path of least resistance, we also know that if there are any closed connections in this circuit, the power supply will establish current throughout the entirety of the circuit, no matter the resistance. So just little things. So as I was saying, we're going to start from away from the battery. And so our battery's on the left. We're going to take our farthest connection, R2 and R3, and combine those first. And so what I'm going to do is combine R2 and R3, and they're in parallel. So I use our equivalent resistance for a parallel connection. So we'll say combining R2 and R3, we get R equivalent for 2 and 3. And so we'll show that 1 over R equivalent for 2 and 3 is equal to 1 over R2 plus 1 over R3. This is just the equation for any parallel connection. So effectively what we've done is we've taken these and combined them to be represented by a single equivalent resistance. And so I can show that what we're really doing is combining R1 and R2 and R3. So here's R1, and this is R equivalent for 2 and 3. And what we've effectively done is made our circuit smaller. Now we have I1, and this new current, maybe we could call it, that's really going to be I2 and I3 before they split, in a sense. So I'm just going to call it, excuse me, I'm going to call it, excuse me, I'm sorry, IC for combine. Now, keeping in mind that this is our given equation, we have a 1 over R equivalent here, so we can't just add these and be done with it. If we were to work with our algebra, we could show by combining these with a common denominator, we could get R3 plus R2 over R3, R2, and then we could invert both sides. So R equivalent for 2 and 3 would be R3 times R2 over R3 plus R2. If we substitute our values, we can solve this. So we would get 83.04 if you calculate this. And so that is the resistance for this picture at that point. But we're not done. We need to now simplify or combine R1 with that equivalent resistance. And they happen to be in parallel. And so we're taking this picture and we're combining R1 and R equivalent for 2 and 3 to get the total R equivalent for the circuit. And so effectively we've simplified this circuit into a simple circuit, but now we need to show or calculate that equivalent resistance. So we would have 1 over R equivalent for the circuit is 1 over R1 plus 1 over R equivalent for 2 and 3. And if we worked through this, we could end up showing that R equivalent for our circuit is 35.2 ohms. And if we know R equivalent for the circuit and V total, we can calculate I total using Ohm's law. So now it's very similar to what we did last time. It just took a little extra work to simplify the circuit. So we know that using Ohm's law, V equals IR, we can get I total. So V total over R equivalent for the circuit is I total So I total would be, and if you calculate everything out, it would be 0.34 amp. In other words, 1/3 of an amp. That means we could also get P total, the total power dissipated by it. P total would just be I total times V total. And if we take 12 volts times 1/3, and it's 0.34, so we round it a little, it'd be 4.09 watts. But we should create a solutions table for this. It probably would have been nice to do this at the beginning, but something to remember about parallel circuits is that the potential difference across each component connected in parallel is the same. In other words, the voltage drop across each of these resistors must be 12 volts. And if you kind of think through this, remembering that the current that leaves the battery must return to the battery, but the circuit must take away all of that potential energy that the battery gave the charges. So if we're following the current through resistor 1, I1 will go through resistor 1 and then back to the battery. That means I1 is going to have to dissipate all of its power, or in other words, transform all of its potential energy as it makes its way through the resistor. So we know I1 must return to the battery with no potential energy. That means R1 must have all 12 volts across it. And the same argument can be made for any of these, because the current passing through each resistor only passes through one resistor. Anyway, that means that our voltage across every component is just 12 volts. They're all in parallel, and they're all connected to the same power supply. Oh, well, in that case, we could just calculate I by dividing V, the 12 volts, by each resistance. And so I'll leave that for you. You can calculate all your I's and all your P's. So fundamentally from this example, it's most important to see that you always want to remember your rules for series and parallel circuits. That's what gave us these answers right away. And you want to always try and simplify your circuit, working from away from the battery in toward the battery. So we started with our farthest connection, combine those, and then we combined the following connection until we had a simple circuit that we could apply Ohm's law and figure more information about it. So that's a parallel circuit example. The next we'll have a combination of the two.